All right, get ready to level up your coding game, because today we're doing a deep dive into something pretty fundamental for any developer who wants to write clean and maintainable code. The solid principles of object-oriented programming.
That's right. These principles are like a set of guidelines that can help you avoid some of those common coding nightmares where a seemingly small change ends up breaking everything.
Exactly. We've all been there, right?
Mhm.
You tweak one little thing, and suddenly the whole system's throwing errors like it's New Year's Eve. So how do these solid principles help us prevent that kind of code catastrophe?
Well, let's start with the first principle, the single responsibility principle, or SRP. Ever worked on a piece of code that felt like it was trying to juggle a million things at
Oh,
once?
yeah, definitely.
That's a classic sign of violating the SRP.
So it's kind of like when you try to cram your entire life into one overstuffed suitcase. Everything gets jumbled, and you can never find what you need.
That's a perfect analogy. The single responsibility principle is all about keeping things organized. It says that each class should have one and only one reason to change.
Okay, so instead of that overstuffed suitcase, we want to pack our code into neat, labeled compartments, each with its own specific purpose.
Exactly. Think of it like having a team of specialists instead of one overworked generalist. If you have one class that's handling calculations, printing, and database interactions, that's like asking one person to be the accountant, the graphic designer, and the IT specialist all at the same time.
Yeah, that person would be totally burned out,
Yeah.
and the code would probably be a mess. So how do we apply SRP in practice? How do we break down those mega classes into more manageable pieces?
Let's say you have a program that generates and manages invoices. Instead of having one giant invoice class that does everything, you could have an invoice calculator class that focuses solely on the calculations, an invoice printer that handles printing, and an invoice repository that takes care of storing and retrieving invoice data from the database.
Okay, so we're basically dividing the workload and giving each class a clear, defined role.
Exactly. And the beauty of this is that if you need to change how invoices are printed, for example, you only need to modify the invoice printer class. The other classes remain untouched, minimizing the risk of unintended consequences.
That's huge, because nobody wants to be the person who makes a small change and accidentally breaks the whole system.
Absolutely. SRP helps us build more robust and maintainable systems by reducing those ripple effects of change.
Okay, SRP makes total sense. It's like a fundamental organizing principle for good code. But how do we make sure our code is not only well organized, but also flexible and adaptable to future changes?
Well, that brings us to our next solid principle, the open-closed principle, or OCP.
Okay, I've heard of this one.
This principle is all about designing your code in a way that allows you to add new features without modifying the existing can.
Wait, hold on. Isn't modifying code like the whole point of programming? How can we add new features without changing the code?
It's not about never changing code. It's about being strategic about where those changes happen. Think about it. When you've got a piece of code that's working perfectly, all tested and stable, the last thing you want to do is go in and start messing with it, right?
Right. If it ain't broke, don't fix it. Right. But how do we add new features without touching that perfectly working code?
That's where the idea of open for expansion but closed for modification comes in. It's about creating structures in your code that allow you to add new functionality by extending your code rather than altering its core logic.
Okay, I'm intrigued, but I need a concrete example. How do we achieve this open for extension magic in the real world?
Let's say you have a notification system that currently only sends emails. Now, you want to add SMS notifications. The traditional approach might involve going into your notification class and adding a bunch of new code to handle SMS.
Yeah, and that could risk introducing bugs into your existing email notification functionality.
Exactly. So what's the OCP way of doing this?
I'm all ears.
Instead of modifying the notification class directly, we can use interfaces and polymorphism. Imagine you have an interface called notifier with a method like send string message.
Yeah.
Then you create separate concrete classes like email notifier and SMS notifier that implement this interface.
So we're creating a contract that different notification types must adhere to, but the actual implementation details are hidden behind this notifier interface.
Exactly. And here's the beauty of it. If you need to add a new notification type like push notifications, you just create a push notifier class that implements the notifier interface. Your core logic for sending notifications remains untouched, minimizing the risk of introducing bugs.
Wow, that's really clever. By using interfaces, we've made our code both open for extension with new notification types and closed for modification to the core notification logic. It's like having a system that's built for the future, ready to adapt to new requirements without breaking a sweat.
That's the power of OCP. It helps you build systems that are not only well organized, but also flexible and resilient to change.
Okay, I'm starting to see how solid principles really take code quality to the next level. SRP helps us create modular and maintainable code, while OCP ensures that our code is extensible and adaptable to future needs. It's like having a blueprint for building robust and elegant software systems. But I have a feeling there's a lot more to uncover.
Oh, absolutely. We've only just scratched the surface of solid. There are 3 more principles waiting to be discovered, each building on the foundation we've laid with SRP and OCP.
All right, I'm ready to dive deeper. What's next on our solid journey?
Let's talk about the Liskov Substitution principle, or LSP. This one's all about making sure that our inheritance hierarchies are sound and that our subclasses behave in a way that's consistent with their parent classes.
Sounds intriguing, but before we jump into that, let's take a moment to recap what we've learned so far. We've covered the single responsibility principle, which is all about
Creating classes that have one and only one reason to change.
right, keeping those classes focused and easy to maintain.
And then we explored the open-closed principle, which encourages us to design systems that are open to extension but closed to those risky modifications that can introduce bugs.
Exactly. It's like we're building a system that's both well-organized and adaptable, like a house with strong foundations and room to grow.
Now let's move on to the Liskov Substitution principle, or LSP. This principle is all about ensuring that our inheritance hierarchies are well-structured and behave predictably. Imagine you have a toolbox full of tools, and they're all labeled as hammers. You'd expect any tool labeled hammer to be able to hammer in a nail, right?
Of course, it would be pretty frustrating if you picked up a hammer only to find out it couldn't actually drive a nail.
Exactly. The Liskov substitution principle is similar. It states that any subclass should be substitutable for its parent class without causing unexpected behavior. In other words, if you have a class bird and a subclass penguin, you should be able to use a penguin object wherever a bird object is expected without breaking anything.
Okay, that makes sense in theory. But in the real world, penguins can't fly, even though they're technically birds. So how do we apply this principle in a way that reflects those real-world nuances?
That's a great point, and it highlights a common pitfall when it comes to LSP. If you have a bird class with a fly method, and then you create a penguin subclass that inherits from bird and overrides fly to throw an error or do nothing, you've essentially violated LSP.
Because now, if you try to use a penguin object wherever a bird object is expected, and the code calls the fly method, you're going to run into trouble.
Precisely. To make this design LSP compliant, we need to think carefully about our inheritance hierarchy. Instead of having penguin directly inherit from bird, we could introduce a new subclass, flying bird, that inherits from bird. Birds that can fly, like sparrows or eagles, would inherit from flying bird, while penguins would remain as a direct subclass of bird without the fly method.
Ah, I see. We're creating a more accurate representation of the real world by distinguishing between birds that can fly and those that can't. Now, any code that expects a bird object can safely handle any subclass of bird, whether it's a flying bird or a flightless bird, without worrying about unexpected behavior.
Exactly. LSP helps us avoid those situations where a subclass breaks the expectations set by its parent class, leading to unpredictable and potentially disastrous results.
Okay, LSP is all about making sure our inheritance hierarchies make sense and behave predictably. It's like making sure all our tools are labeled correctly so we can use them effectively without any surprises. But inheritance is just one aspect of object-oriented programming. What about interfaces? How do solid principles guide us in designing good interfaces?
That's a great question, and it brings us to our next principle, the Interface Segregation Principle, or ISP. This principle is all about avoiding bloated interfaces. Have you ever worked with an interface that had a ton of methods, many of which you never actually used in your implementation?
Oh, absolutely. It's like having a Swiss Army knife. When all you need is a simple screwdriver, you end up carrying around all this extra bulk that you never actually use.
Exactly. The interface segregation principle is like saying, let's break down that Swiss Army knife into smaller, more specialized tools. It states that clients should not be forced to depend on methods they don't use.
So instead of having one giant interface that tries to do everything, we want to create smaller, more focused interfaces that cater to specific needs. Can you give us an example of how this works in practice?
Let's imagine you have an interface called Machine with methods for printing, scanning, and faxing. Now, if you have a class that only needs the printing functionality, it still has to implement all 3 methods, even though it doesn't need scanning or faxing. This leads to unnecessary code and complexity.
I see the problem. It's like forcing a class to implement methods it doesn't need just to satisfy a bloated interface. It's inefficient and makes the code harder to understand.
Exactly. The solution, according to ISP, is to break down this large interface into smaller, more specific interfaces. You could have a printer interface with only the print method, a scanner interface with the scan method, and a fax interface with the fax method.
So instead of having one massive interface that tries to be everything to everyone, we have three streamlined interfaces that focus on specific tasks.
Precisely. This way, a class that only needs to print can implement the printer interface without the baggage of unnecessary methods.
Okay, ISP is all about keeping our interfaces lean and mean, providing just the right amount of functionality without forcing classes to implement methods they don't need. It's about clarity, efficiency, and making sure our code is easy to work with.
Now, there's one more principle that ties all of these concepts together and helps us create truly flexible and adaptable systems.
Okay, I'm ready for it. What's the final piece of the solid puzzle?
It's called the Dependency Inversion Principle, or DIP. And this one can be a little mind-bending, but it's incredibly powerful.
All right, bring it on. I'm ready to have my mind bent. What is this dependency inversion principle all about?
The Dependency Inversion Principle is all about decoupling our code. It states that high-level modules should not depend on low-level modules. Both should depend on abstractions.
Okay, I need you to break that down for me. What are high-level and low-level modules in this context?
Think of it this way. High-level modules are the parts of your code that contain your core business logic, the brains of your application. Low-level modules are the nuts and bolts, the things that handle details like database interactions, network communication, or user interface elements. DIP says that both of these should depend on abstractions like interfaces rather than concrete implementations.
So instead of having a direct dependency between a high-level module and a low-level module, we introduce an interface that acts as a middleman. Why is that so important?
Because it allows us to swap out different implementations without affecting the core logic of our application. Imagine you have a computer class that uses a keyboard class. If the computer class directly depends on a concrete standard keyboard class, you're tightly coupling your code.
So if you later decide to use a mechanical keyboard instead, you'd have to go into the computer class and change the code to work with the new keyboard type. That sounds like a lot of work, and it could potentially introduce bugs.
Exactly. That's why DIP is so crucial. To follow DIP, we would introduce a keyboard interface that both standard keyboard and mechanical keyboard would implement. The computer class would then depend on this keyboard interface, not on any specific implementation.
Ah, I see. So now the computer class doesn't care what specific type of keyboard is being used as long as it adheres to the keyboard interface. That makes the code much more flexible and adaptable.
Precisely. DIP gives us the freedom to swap out different implementations without breaking our core logic. It's like having a system where you can easily upgrade or replace components without having to rewire everything.
This is amazing. I'm starting to see how all these solid principles work together to create code that's not only well organized, but also flexible, adaptable, and resistant to those pesky bugs that always seem to pop up at the worst possible time.
It's like having a toolbox full of the right tools and knowing exactly how to use them to build something truly robust and elegant.
Exactly. SRP helps us create modular classes. OCP ensures that our code is extensible. LSP makes sure our inheritance hierarchies are sound. ISP keeps our interfaces lean and focused. And DIP helps us decouple our code and make it more flexible. Together, these principles provide a framework for writing code that's a joy to work with, both now and in the future.
And they can help you avoid those coding nightmares where a simple change ends up breaking everything.
Exactly. Solid principles are like a superpower for developers, allowing us to create code that's not only functional, but also beautiful, maintainable, and built to last. But before we wrap up our deep dive, I think it would be great to hear your final thoughts on how all of these principles come together to make us better developers.
Absolutely. Solid principles are more than just a set of rules. They represent a way of thinking about software design that can truly elevate your craft. Applying these principles can seem like extra effort up front, but the payoff comes in the form of more robust, maintainable, and scalable systems.
Okay, so what's the key takeaway for our listeners? What's the one thing you want them to remember about solid principles?
Okay, so what's the key takeaway for our listeners? What's the one thing you want them to remember about solid principles? It's this. Think of solid principles like building a house with strong foundations. Each principle contributes to a different aspect of the structure, but they all work together to create a stable and maintainable result.
Okay, I love that analogy. We've talked about how SRP is about creating well-defined modules, like laying the groundwork. Then
Mm.
OCP is about making those modules extensible, almost like adding windows and doors so the house can breathe and grow.
Exactly. Then LSP ensures our inheritance hierarchies sound like making sure the walls are straight and the roof is sturdy. And we can't forget about ISP, which keeps our interfaces lean and focused, like efficient plumbing and electrical systems.
Right, and then DIP swoops in to help us decouple our code and make it more flexible. Kind of like having modular furniture you can rearrange easily as your needs change.
That's a great way to put it. Solid principles provide a blueprint for building software that's not just functional, but also adaptable and resilient to change.